want to address what might appear to be a minor point. In how the slope of the water table affects the pore pressure and how we write the factor of safety equation as a result of that. Let's start with a very basic principle of water flow and groundwater flow in particular. It says that water flows in the direction perpendicular to lines of equipotential, where that potential is defined as the total head. So total head is, let's call it capital Phi, and that equals the elevation head plus the pressure head. In the case where I have water flowing, say, through a tube in this direction, then my equipotential lines, and let's say in this ideal case I have frictionless walls, my equipotential lines are perpendicular to the walls of that tube. If my water is not moving, and I have a horizontal water table, then there are no equipotential lines because everything is at the same potential. If this is, for example, a pond, or that's trying to be a bit of a perspective view to indicate it's a pond and not a cross-section of a flowing body of water, then again, all the water in that pond has the same potential. If it didn't, it would be moving. It's not moving, so it's all the same potential. Okay. Well, let's look at a couple of cases then. Let's look at a static case and a dynamic case. That is, one in which the water is not flowing and one in which the water is flowing. In both cases, we'll have our Earth's surface, and I'll draw a dashed line as a potential failure plane at which I want to do my stress calculations. My coordinate system is oriented with the x-axis parallel to that dashed line. My z-axis then is normal to that dashed line and normal to the surface. Now, if my water's not moving, I need something to hold it in, right? I'm going to have to cap it, so let me put a cap on the end. And let's call that my impermeable barrier. And in that case, I can have a water table that is horizontal, not moving, held up by that impermeable barrier. Let me just go ahead and draw in contrast to that the dynamic case. Same coordinate system. By the way, this angle here is theta, same as this angle here. But in this case, the water is moving, and it is moving. If the water is moving parallel to the surface, which we're going to assume that it is, then my water table also has to be parallel to the surface. Okay, no impermeable barrier. This water is moving, this water is not. Let's look at the pressure head at a test point. I'll put my test point right here, and these aren't exactly lined up. I'll put my test point right here, down here. So that's my test point up there. There's my test point down there. I want to know the total head with that test point. Well, actually, what I'm really going to be concerned with is the pressure head, and really for my stress balance, the pressure, not just the pressure head. Again, total head, elevation head plus pressure head, we'll be using that. What is my pressure right there? Pressure at the first test point, at the static test point, is, well, in this case, it's the depth of the water over that point. Now, I'm going to be a little weird about it though. Instead of just drawing a thickness representing that depth, I'm going to draw a thickness h sub w that is actually normal to the surface and the potential failure plane. Do the same down here. So what's my pressure at that point? My pressure is, again, the height of the water table above that point. Well, with the height of the water table above that point, we have to get through trig. So that height, well, it forms part of a right triangle for which the HW line is the hypotenuse. So we can use our geometry to realize that this angle is theta, same as this angle. And so this height above the test point, height of the water table above the test point is the hypotenuse times the cosine of that angle. Okay, so that means my pressure at that static point is density of water, rho sub w, times acceleration due to gravity, times h sub w cosine theta. In this case, in the static case, what matters is that vertical distance below the free water surface. Now, in the case where we're letting the water flow, again, flow is perpendicular to lines of equal head, so these are perpendicular to the surface. So let me go ahead and draw in those equipotential lines. Those are my equipotential lines. If I'm trying to get total head and draw some comparisons here, I'm going to look at the elevation head at this. I'm going to measure it at that point. So let me draw in an elevation, and I'm going to call that z prime. And that's just relative to some arbitrary datum. Similarly down here. And that's supposed to be a capital Z. And Z prime, because this Z it's oriented in a different direction than this Z here. Well, in this case, what's my total head? In the static case, my total head, capital phi, is Z prime. And it's the same everywhere. So in the static case, my total head is Z prime. If I'm below the surface some distance, let's say here, then my total head would be, say, Z prime minus the elevation change plus the pressure head. The pressure head in that case is equal to that height of the water table above the test point. So in this case, let's be clear, my pressure head is is the pressure divided by density and acceleration due to gravity. And so the pressure head in that case, HW times cosine theta. So we're going down to again to the dynamic case, and in that case, again, flow perpendicular to lines of equipotential. Let's look at the total head at a couple of points. At the water table, my total head, phi Wt for water table, is simply the elevation. Right? No pressure because I'm pressure 0. That's how we define the water table in the first place. So total head at the water table is just the elevation head Z prime. Maybe I haven't drawn this quite right, but HW is supposed to be parallel, or that line representing that thickness is supposed to be parallel to my lines of equipotential, and so the total head at my test point has to be the same as the total head at the water table. So I know that my total head at the test point, E sub Tp, is also equal to Z prime. That is a resultant of the elevation head plus pressure head. So let's break it down. What is my pressure? What is my elevation head? You know, I know the right answer ahead of time, but what is my elevation head? Well, my elevation head is simply z prime minus this distance right here. Right angle, angle theta, hw there, hypotenuse, and so that distance there is hw times cosine theta. My elevation head at my test point is z prime minus hw cosine theta. Therefore, my total head is elevation head plus pressure head. I'm going to use the general expression here for my pressure head, where I'm defining it in terms of the pore pressure. Elevation head z prime minus hw cosine theta plus my pressure head. Well, I know that this quantity is equal to z prime because I just know that. I set it right here. So set that equal to z prime. Well, I've got z prime now on both sides. I can cancel those. And I'm left with 0 on this side, negative hw cosine theta plus u over rho wg equals 0. And I can solve that for my pore pressure, because the whole point of this was, gee, what's my pore pressure in this case where I've got a slanted water table? Get rid of my z prime there, replace that with 0, get rid of that z prime there, and I'm going to get rid of this because I'm going to want to do a little bit of algebra on here. Okay, so I have now this equality, and I can solve this for u. Alright, so let's do the algebra here. Add hw cosine theta to both sides, and I get those canceling out there. I have now this, and I can multiply both sides by rho w times g. Get rid of that 0 there, so I don't need that. Multiply both sides by rho wg. Cancels on this side. Go ahead and just erase them. Neaten this up. Erase, get rid of that. And I've got my answer. Pore pressure is equal to rho w times g times hw times cosine theta. That is different from what appears in our book in equation 10.55 in the Anderson and Anderson book. I'm confident in this physical argument, and therefore the book is wrong in that regard. And that means that the factor of safety equation that I have is different from the one in the book. That means compared to the equation that we have in our book, in the Anderson and Anderson book, my factor of safety equation is still off by a factor of cosine theta on the soil depth. And that's because the book uses vertical depths, whereas mine are slope normal thicknesses. If we use vertical depth of soil and water, then we have to divide by a factor of cosine theta. Let me just draw in, so my vertical, I'll use a lowercase h w for the water table height, and a lowercase h for the vertical soil depth, whereas the slope normal soil depth is capital H. It's pretty straightforward to see that. In this case, small h is equal to big H over cosine theta. Remember, cosine theta is a number between 0 and 1, and so to get the bigger number, I divide the smaller number by a number less than 1. Okay. Similarly, for the water table vertical thickness, is big HW over cosine theta. Again, what's the factor of safety? Factor of safety is the ratio of magnitude of the shear strength to the shear stress at a point. So my shear strength is, okay, the effective normal stress times the coefficient of friction plus cohesion divided by, then of course, the shear stress. Okay, so that is, we'll use sigma, lowercase sigma for our normal stress, subtracting pore pressure. So that quantity, the effect, that's what we would term the effective normal stress. Multiply that by the coefficient of friction, tan phi, add cohesion, just use a lowercase c, and divide by the shear stress. Alright, so I've rewritten the results from before over here, and I just want to review how we get this factor of safety equation. So we will have our inclined surface with bedrock below it, our coordinate system, which the x-axis is parallel to the bedrock surface, and the soil surface is the axis perpendicular. And we want to look at stress balance at a point at the bedrock soil interface. We've got the weight per per unit area going straight down. Now we've got an angle theta here. So here's our weight. That weight per unit area is bulk density times gravity times soil thickness, where our soil thickness is measured parallel to the z-axis. Similarly, a water table, or a saturated thickness, also measured normal to the surface. In order to get these terms, I need the sigma. I have the pore pressure from before. I need the sigma. I need the tau, or shear stress, normal stress. Okay, so it helps to draw a rectangle for which the weight is the diagonal, and one side of the rectangle is then the normal stress, the other side of the rectangle is the shear stress. We start with the normal stress. The normal stress is simply the weight times this angle cosine of that angle, which is the same as that angle. So sigma equals bulk density times gravity times soil thickness times cosine theta. And the shear stress is simply the unit weight times the sine of that angle. Now I have enough to rewrite my factor of safety equation. I can see that with the normal stress and the pore pressure, I've got common terms of cosine and gravity, so I can go ahead and pull those out. So within the parentheses I have bulk density times soil thickness minus water density times saturated thickness times gravity and cosine. And that's my normal stress, my effective normal stress, and then I multiply that by tan phi, the friction coefficient, to get the strength resisting the shear stress. Of course, I need cohesion as well. And then I divide by the shear stress. Now, if I want to use vertical depths and saturated thicknesses, then I simply make the substitution for h equals little h cosine theta and hw equals little hw cosine theta in this formula here. And so I can rewrite this as density times little h w. I'm going to pull that cosine since it's in both of those terms. I'm going to pull it out, so I've got my gravity. Now I'm going to have a cosine in addition to the one that's already there. Cosine squared theta tan phi c. And here I will also have cosine. And so we see we get an extra cosine down here. We also get an extra cosine up here. The extra cosine in this case is due to shifting to vertical from normal. The original cosine that appears here, for example, so the cosine here with respect to the normal stress comes from using the slope normal component of the weight, and the cosine having to do with the pore pressure comes from the fact that the water is flowing rather than flat, or rather than not flowing. Quick bit here about slope hydrology. So we've drawn a conceptual basin watershed here that is flowing through a cross section here. Now and we can draw it two ways. We can draw it so that the plane through which it's flowing is normal to the surface, or where the plane is vertical. I generally prefer the normal orientation, that is perpendicular to the surface. But let me go through the implications of doing one versus the other, with a focus on my preferred way. So first let's look at calculating the head gradient. Here I'm representing total head with a capital phi, and we have then d phi dx, where x is oriented parallel to the slope, is the difference in elevation of the water table with respect to a delta x. Okay, now why the elevation of the water table? Because total head in general is elevation head plus pressure head, and at the water table pressure is 0, so that's where we can absolutely simply use the elevation. And that's generally what we do in groundwater, at least for unconfined aquifers. Okay, so here we've got z1 prime, again my z prime, because this is a vertical z rather than a slope normal z as in my coordinate system. So I've got z1 prime, z2 prime. Those are the two elevations at distances separated by a delta x, again where x is parallel to the surface. So here's our head gradient. Now, okay, so let's draw the triangle. I've blown this bit up a little bit. So here's my delta x, showing angle theta for this triangle, and then the length of this side is simply z1 minus z2, or z1 prime, sorry, minus z2 prime. And if I have a unit delta x, then that means my d phi dx is negative sine theta. Okay, so again for a unit hypotenuse, I've got a right triangle. Here's my theta. The side opposite it for a unit hypotenuse is sine of the angle, or in this case negative sine of the angle, since the angle is strictly speaking negative in that case. All right, or we could orient axes z prime vertical, x prime horizontal. In that case, we need to transform well, we'd have delta x prime equal to delta x times cosine theta, and dx equal dx prime divided by cosine theta. So that my d phi dx becomes cosine theta times d phi dx prime. D phi dx prime now, where I've got my delta x, the horizontal, in this case where if I have a unit hypotenuse and an angle theta here, then my slope is the ratio of sine to cosine. The ratio of this side to this side is sine over cosine, that is its tangent theta, and here I've put in the negative sign. Of course, tangent theta is sine over cosine, so the cosines cancel and we end up back where we must, really, with the head gradient equal to minus sine theta. Regardless of the coordinate system, we have to have the same result. Now let's look at, okay, we've got either we can do this again two ways. We can look at H as a soil, big H as a soil thickness, big H sub W as a saturated thickness, or we can use vertical little h and little hw. At our cross section we have a contour width W. Now note that because this isn't a perfect tube or whatever, or half pipe, that as soon as we reorient the plane a little bit, it's going to depend, that width may in general change, but let's just assume that it doesn't change such that we need to worry too much about it. Okay, so we've got from Darcy that the discharge is going to be the cross-sectional area of flow. Note that this is H sub W times width. That is, the flow can only go through the saturated bit. We're talking about saturated hydraulic conductivity. Above the water table, we only get vertical infiltration, vertical seepage. Only below the water table does the flow run parallel to the water table. All right, and then we've got our minus d phi dx here as our head gradient. And then that simplifies out to saturated hydraulic conductivity times the cross-section width times the saturated thickness times sine theta. We can write it also in terms of little hw, in which case we need to throw in another cosine theta because this is our substitution right here, right? In place of big H sub W, we put in little h sub W times cosine theta. Okay, so there's our Q according to Darcy's law. According to continuity, we have discharge equal to precipitation rate times contributing area. All right, so we've got contributing area A, dimensions L squared. This is generally assumed projected onto a horizontal plane, as if we were reading the area or measuring the area from a map. And precipitation rate P, as units of length over time, generally assumed to be falling vertically. Okay, so in this case we're looking at the projection of this area onto a horizontal plane, and it's getting hit by vertical rainfall. This is important to just note that this is at steady state where it's been raining forever and I've got that same precipitation rate forever, and so this is necessarily my discharge through this cross section. That's steady state. So since infiltration is also vertical, there is a slight discrepancy at this cross section of interest. A little bit of the rain falling on the area reaches the water table downslope of the cross section. Oh well, we just got to deal with that. It's no big deal. I mean, if we were dealing with a very small contributing area, it might be something that we needed to worry about. In this case, we're assuming that that A is much larger than this little area there. All right, so we set the two discharges equal. Ksat W HW sine theta equals PA, and we solve for the saturated thickness, and here's our result. Precipitation rate times contributing area divided by saturated hydraulic conductivity and width and sine theta. Now, if we were using a vertical plane, i.e. a cross-section area, our cross-section area is W times little hw, which is equal to W times big HW divided by cosine theta, then we also account for the flow direction not being perpendicular to the plane, and we have to throw in another cosine theta here. Or, no, sorry, that's our cosine theta from here. We have to throw in another cosine theta out here. So if we substitute in for little h sub w, the big HW over cosine theta, then we've got our head gradient sine theta. We're essentially compensating for the fact that the flow vector is not perpendicular to the plane, and so we're essentially finding that component of it that is perpendicular to the plane, and to do that we multiply by cosine theta. And so cosine theta comes in here, cancels the cosine theta underneath the h sub w, and we end up with the same result for Q. Again, as we must, because physics is still physics regardless of our coordinate system. One of the things that might tend to complicate our view on how this is all supposed to work is that commonly in groundwater we do essentially use an x-axis that is horizontal, and we assume that the slope of the water table is so small that the difference between the horizontal and the tilted water table doesn't matter. And so when we define our head gradient as d phi dx, if dx is horizontal, well, Darcy's law says that the distance, the relevant incremental distance, is along the flow path. In general, in big aquifer type problems, that flow path is so close, that flow vector is so close to horizontal that the difference doesn't matter, and so we generally blow it off. In this case, maybe it's not blow-offable, because we may be dealing with a slope that's, say, between 30 and 40 degrees, and in that case there is a significant difference between the flow vector direction and the x and a horizontal direction, and so we do kind of need to take these things into account. But it's one of these things that we get used to. If we're used to doing groundwater problems, we get used to making that assumption that the flow vector is nearly horizontal and near enough to horizontal that we don't need to worry about it. It's in these steep slopes kinds of situations that kind of approximation is no longer very good, and we do need to do things kind of by the book.